Okay then, welcome back here for our second video on the Chapter 12 practice test. In this video, we're going to look at questions 4 through 8. So, an old saying in golf is, you drive for show, you putt for the dough. The point is that good putting is more important than long driving for shooting low scores and hence winning money. To see if this is the case, data from a random sample of 69 of the nearly 1,000 players on the PGA Tour's World Money List are examined. The average number of putts per hole, fewer is better, and the players' total winning for the previous season are recorded, and a least squares regression line is fitted to the data. Assume that the conditions for inference about slope are met, and below is a computer output for the regression analysis. So the first thing I want to do here is kind of pick apart all of what we see here. This first number here under constant, or next to constant and under coefficient, that is A, the y-intercept. We learned that in Chapter 3. The next three numbers in that same row, well, those are actually going to be unused. At least they're going to be unused for AP statistics. In the second line, with average putts, we have that negative, what is that, 4,139,198. That is the slope of the regression line. Next to that, we have SEB, which is a standard error of B. Then we have the test statistic, which is not given. Next to that, also not given, is the p-value for the two-tailed alternative. Finally, you have in the last row the standard deviation of the residuals. Next to that, we have the value of r squared. And remember that r is equal to the negative square root of r squared in this case, because our slope b is negative. And that's followed by r square adjusted, which we're not going to be using in AP statistics. Okay, with all of that here, by about how much does a sample slope typically vary from the population slope in a repeated random sample of 69 golfers? Well, for this one, we're going to be looking for the standard error of B, which we already know from our chart. It's letter B. Okay, the next one. Suppose that the researchers want to test the hypothesis beta equals 0 versus beta is less than 0, or beta 1 is equal to 0 versus beta 1 is less than 0. Which is the following of the test statistic, and interestingly, they don't actually give you, well, not interestingly, but they don't give you the actual test statistic here. It's been starred out, I guess is the correct way to do that. But that's not a big deal because we know the formula here for that test statistic. The test statistic is B minus beta over SEB. And most of the numbers necessary for us to calculate this are actually given to us already in the problem. This gives us a value of negative 2.437, which rounds to letter E. Number 6, the p-value is 0.0087 for the test of the hypothesis beta equals 0 versus beta is less than 0. So what is the correct interpretation of this result? So we got to be a little bit careful here. Are we interpreting the p-value, or are we interpreting the p-value, or are we interpreting the p-value in terms of what that says for this test? So let's read through the combinations here. The probability that there is no linear relationship between the average number of putts per hole and the winnings of the 69 players is 0.0087. And that's a gross simplification of what that p-value is. Now that p-value makes the assumption that the null hypothesis is true. So in this case, there is an assumption that beta is actually equal to 0. And then the p-value would be the probability of obtaining a value of b. That is the value that we got, that negative 4 million number, or smaller than that $4 million number. So that's an incorrect answer. Letter B, if there's no relationship between the average number of putts per hole and the total winnings of players on the PGA Tour's World Money List, now that right there was just a summary of beta equals 0, or an interpretation of beta equals 0. So the probability of getting a random sample of 69 players that yields a least squares regression line with a slope of negative 4 million or less is 0.087. Now that sounds like a really good answer. It's in context. It tells us, assuming that the null hypothesis is true. So everything here looks pretty good. Letter C, the probability of making a type 1 error is 0.087. Nope. Letter C is conflating p-value and alpha. Alpha is the probability of making a type 1 error, not the p-value. Letter D, if there's no linear relationship between the average number of putts per hole and the total winnings for the players in the sample, the probability of getting a random sample of 69 players that yields the least squares regression line with a slope of negative 4,139,198 or less is 0.0087. And if you're reading this and thinking, wait, didn't I just read that in letter B? I just did the exact same thing. But take a close reading here. This one says players on the PGA Tour, which would be the population. And this one just says players in the sample. So that right there makes all the difference here. We need to take a look at no linear relationship in the population, not in the sample. So a close reading is necessary here to rule out letter D. In letter E, the probability that there is no linear relationship between the average number of putts per hole and the winnings for all players in the PGA Tour's World Money List is 0.0087. Just like letter A, this is an oversimplification of the p-value. P-value's interpretation needs to state something about the null hypothesis being true. And there's nothing about that here. Right, so I don't think there's a whole lot to say here. Let's move on to question 7, which is the following is a 95% confidence interval for the slope of beta 1, the population regression line. Well, the first thing we can rule out are probably letters D and letters E. Both of these two options have the incorrect value of B. And if we take a look here, the value of B is at negative 4,139,000, not positive 7 million. So those are not correct just based on the value of B. The next thing that we're looking at is, okay, well, these both have the same value. All three of these have that same value for standard error of B. It happens to be correct, but that would have been the next thing I'm going to look at. And so the last thing that we can do here is take a look, and they all have different values of T star. So we got to get the correct value of T star in order to get this one correct. So grabbing my calculator, we can go to the inverse T, and we want a 95% confidence interval So we're going to do 1 minus 0.95 divided by the 2. That's going to give me the left tail. There were a total of 69 golfers minus 2. In other words, there were 69 values for the number of putts, and there were also 69 values for the winnings. So 69 pairs of coordinate data. We'll go ahead and calculate that, and this should be pretty conclusive here. Yep. You see, it looks like a p-value of not a p-value, a t-star of positive 2. So our correct answer here should be letter C. All right, let's move on to question 8. This is going to be the last problem in this video. We've got which of the following would make the calculation of the 95% confidence interval invalid? So this is a question about the conditions for a test. So we're going to go back. We're going to review what those were. The conditions for a test: linear scatter plot, no pattern in the residuals, 10% independence or 10% condition, normal residuals, the dot plot of the residuals needs to have no strong skews and outliers, equal standard deviation, residuals do not increase or decrease in size, and then random sample. So coming back to this question here, let's put our reminder of linear. So we're going to take these apart one by one, hopefully. And letter A, if the distribution of earnings wasn't approximately normal, then the interval would be invalid, or the conditions would be violated. And earnings, if we remember that correctly, earnings were the dependent variable. And there's nothing here that says that the dependent variable needs to be approximately normal. The residuals need to be approximately normal, or not distinctly non-normal, but nothing about the dependent variable being normal. Letter B, if the earnings for golfers with small putting averages was more variable than the earnings for golfers with large putt values, then that would seem as though residuals for small putting averages were larger than residuals for the large putting averages. This one seems like it's going to be our winner here, but of course we're going to keep on going. Equal standard deviations, if you violate that, then you have violated letter E. But we're going to keep going. If the standard deviation of earnings is much larger than the standard deviations of putting averages. What's really happening here is this question says we're comparing standard deviation of y and the standard deviation of x. Now, there's nothing in our conditions that say that one standard deviation has to be less than the other, so letter C is not correct. Letter D, the distribution of earnings has an outlier. Well, residuals, as we can see for condition N, residuals can't have large outliers. However, the dependent variable, which in this case is the earnings, that could be an outlier, especially if we consider that by the nature of these linear regressions, the dependent variable may be growing, increasing or decreasing. So it's possible that you'll have a dependent variable that's either way too large or way too small. Especially if you're comparing the dependent variable with other values of the dependent variable. And letter E, what about if the sample data isn't perfectly linear? And actually, that's not a problem. In fact, you're probably never going to see actual sample data that is perfectly linear. So this isn't a problem. Otherwise, we would, if it was perfectly linear, if the sample data was perfectly linear, then we probably wouldn't be doing a test on the linear regression or a test on the value of b because, well, we'd already have a really good idea about that. So that takes care of questions, what did we do, numbers 4 through 8. And that concludes this video. We'll see you for the remaining 2 questions here on the multiple choice section of the Chapter 12 practice test. Have a good one.